Heads-up Experience, or HUX, is a pioneering AI system that serves as a constant companion in human-environment interaction. It bridges the gap between digital and physical domains by utilizing eye gaze tracking, environmental analysis, and verbal context interpretation to capture and enhance multimodal data in real time. This approach enables more natural, empathetic, and intelligent interactions between the user and HUX AI, particularly when deployed in smart glasses and extended reality headsets. The paper outlines the potential of HUX AI to revolutionize human-computer environment interaction, paving the way for future advancements in this field. The research aims to develop an advanced AI companion for daily life, integrating digital assistance with physical world interactions. This technology seeks to revolutionize human-AI collaboration in both personal and professional settings, paving the way for the future of personal smart devices. The concept involves enhancing interactions through embodied AI, leveraging multimodal memory, and real-time video processing. Eye gaze tracking is a key component, as illustrated in Figure 1. This innovation has the potential to significantly impact the field of human-computer environment interaction, particularly with the integration of VLM and LLM. The HUX AI system integrates vision language models, large language models, and large action models to implement human-computer environment interaction principles. This enables a more intuitive and immersive user experience, surpassing traditional graphical user interfaces. A HUX device, which can be a custom setup, smart glass, or extended reality headsets, features multiple input and output modalities. These include speech and gaze for user inputs, scene inputs from the environment, and display and speech outputs. The primary goal of the HUX AI is to assist users in accomplishing their tasks of interest by providing real-time information and guidance. In task-specific scenarios, objects of interest are crucial, as they directly or indirectly affect the task outcome. The HUX AI continuously tracks these objects' existence, position, behavior, and other relevant aspects. This information is then used to generate appropriate responses or actions that aid the user in completing their task efficiently. The system also identifies events of interest within the environment, which could potentially impact the task at hand. By detecting these events and adjusting its responses accordingly, the HUX AI ensures a seamless and adaptive interaction between the user and their environment. The HUX AI's capabilities are further enhanced by its ability to define regions of interest within the user's field of view. This allows the system to focus on the most relevant parts of the environment, reducing processing overhead and improving response times. By leveraging advanced technologies and focusing on the user's task of interest, the HUX AI provides an immersive and intuitive experience that transcends traditional GUIs, revolutionizing human-computer interaction. Next-generation personal smart devices, PSD, require significant advancements in human-computer environment interaction, HCEI, to provide seamless user experiences. These devices must be capable of understanding human-environment interactions, enhancing both input and output modalities. To achieve this, a real-time video analyzer is employed to detect events of interest, EOI, which are significant occurrences that help in understanding the sequence of temporal changes and their impacts. Additionally, multimodal context processing is utilized to provide context-aware answers. A crucial aspect of this process is the identification of the region of interest, ROI, which focuses attention on specific areas, enabling devices to prioritize and process relevant information efficiently. By integrating these technologies, PSDs can better comprehend and respond to user interactions, ultimately enhancing overall performance and user satisfaction. The recent advancements in transformer-based language and vision models have demonstrated human-like contextual understanding capabilities, paving the way for the development of user-centric AI systems that enhance human-computer environmental interaction, HCEI. By leveraging these models and multiple input modalities, the goal is to create a system that aligns its perception with how users perceive the world, reducing friction in human-computer interaction, HCI, and minimizing the need for human articulation. The extended reality headset or smart glasses are identified as the ideal deployment platforms for these AI systems due to their proximity to human perception and communicative sense organs. This proximity enables the AI system to access user perception data, facilitating intuitive communication. The paper focuses on the design of subprocesses and their integration to assemble a prototype HUX AI system. This work aims to build a PSD with integrated AI, moving beyond the current graphical user interface (GUI)-centric approach in PSD. The paper is organized to provide a comparative analysis with existing literature, a problem statement, a description of the heads-up experience, HUX AI architecture, applications of HUX AI, experiments, discussion, limitations, and future works, and concluding remarks. Comparative analysis with existing literature reveals that selective attention theory plays a crucial role in cognitive processing. This theory enables individuals to focus on specific stimuli while ignoring irrelevant information. Influential models, such as the broad-bent filter model, propose an early selection filter that processes inputs based on their physical characteristics. The Treisman attenuation model refines this idea, suggesting that unattended messages are attenuated rather than completely filtered out, allowing some level of further processing. In contrast, the Deutsch and Deutsch late selection theory proposes that all stimuli are processed meaningfully before selection occurs. The Levy load theory integrates elements of both early and late selection, suggesting that attentional selection depends on the perceptual load of the task. Addressing the limitations of selective attention is critical for three primary reasons. Firstly, enhanced safety is essential in high-stakes environments such as healthcare, aviation, and security, where missing critical information can have serious consequences. Secondly, improved decision-making is facilitated by comprehensive awareness of the environment, leading to better informed decisions in both professional and everyday contexts. Finally, reducing the cognitive load on individuals allows them to focus on their primary tasks effectively, improving overall productivity. The significance of addressing selective attention limitations cannot be overstated, as it is essential for achieving these benefits. This analysis has important implications for video processing, visual enhancement in extended reality, embodied AI, and multi-modal HUX AI. By understanding the mechanisms of selective attention, researchers can develop more effective strategies for information processing and presentation, ultimately leading to improved performance and safety in various domains. The HUX AI system is designed to augment human awareness through real-time human-AI collaboration, building on theories of selective attention. It observes objects and events of interest in the environment, providing additional contextual awareness to support better informed decision-making. This context-aware system enables humans to have conversations with AI about other phenomena in the environment, leveraging real-time contextual data processing and scene understanding. For video processing, the authors employ events of interest, EOIs, based frames, utilizing deep learning models such as YOLO to analyze real-time video and extract EOIs using objects of interest, OOIs. This approach enhances the signal-to-noise ratio, deriving meaningful signals from raw data and reducing computational costs associated with vision language models. The authors also explore visual enhancement in extended reality, achieving this through holographic labeling using AR algorithms and deep learning-based algorithms. YOLO models play a crucial role in extracting EOIs in real-time video analysis and can also be used for OOIs labeling in the scene, offering dual benefits. The authors draw on existing work, such as the MR system presented in 12, which implements real-time object detection and tracking using Microsoft HoloLens. Building upon the concept of superimposing holographic labels on detected objects, this research enhances extended reality experiences by feeding scene perception into a visual language model, VLM, with task-specific object of interest, OOI, labeling. This allows the HUX AI to perceive the scene as the user does in a task-specific scenario, without fine-tuning the VLM for this purpose. In the context of embodied AI, human-computer interaction, HUX AI, systems like Humane Pin and RabbitR1 leverage VLMs to interpret and interact with dynamic scenes, providing an intuitive and responsive user experience. Similarly, this research utilizes VLMs to understand dynamic scenes in HUX AI environments, akin to the approach demonstrated in AutoRT for scene understanding and grounding in robotics. Recent advancements in gaze-facilitated information querying systems have opened up new avenues for natural and intuitive HUX AI. The GVOILA paradigm combines users' gaze data, visual field, and voice-based natural language queries to facilitate intuitive information retrieval in daily scenarios, revealing user query behavior patterns, including ambiguous expressions and specific eye movement patterns associated with querying tasks. In contrast, the HUX AI implementation extends multimodal querying into a dynamic and real-time task-specific environment, incorporating active change detection, real-time environmental adaptation, and personalized context memory to address identified challenges. This approach enables the HUX AI to perceive the scene in a more human-like manner, enhancing the overall extended reality experience. The authors emphasize the importance of integrating gaze-enhanced features and multimodal capabilities in human-computer environment interaction (HCEI) systems. This integration aims to resolve query ambiguities and adapt to users' situational context, building upon previous research such as 14. The system is evaluated through a real-time test environment that undergoes continuous changes, simulating real-world interactions with smart glasses equipped with HUX AI. The problem statement highlights the need for personal cognitive devices, PSDs, to aid humans in real-world scenarios, extending beyond digital expertise to facilitate human-environment interaction, navigation, and complex domain-specific tasks. The goal is to enhance user productivity, decision-making, and understanding in diverse environments, making the PSD a general-purpose AI. Current tools are often confined to specific domains and devices, limiting their utility. The authors aim to create a PSD that can be effectively utilized across various scenarios, thereby increasing its overall utility. The proposed system is designed to track multimodal data, including scene changes, gaze changes spatially and temporally, and contextual user interactions. This real-time testing environment enables the evaluation of the system's efficacy in responding to user queries and adapting to changing environments. AI-enabled devices have the potential to significantly enhance user capabilities across various daily tasks. The distinction between domain-specific models and generalist models is crucial in understanding their functionalities. HUX AI, a system that integrates a generalist base with modular, task-specific layers, offers flexibility and specialization for diverse applications. The importance of collaboration and the need for wearables to augment user capabilities are emphasized. Table 1 outlines the HUX AI agenda, focusing on expertise in a primary task and proficiency in multiple daily tasks to promote regular use and broad applicability throughout the day. This approach encourages users to leverage AI technology consistently, leading to more efficient and effective daily routines. The AI utility of HUX AI is defined as the product of the number of domains and domain-specific task performance, indicating the magnitude of its usefulness in a particular task. This is visualized in Figure 2, where domain-specific models are optimized for precise tasks, represented by green dots, and generalist models offer broad language understanding and generation, represented by orange dots. The HUX AI integrates a generalist base with modular and task-specific layers, enabling flexible and specialized applications. The utility of HUX AI is determined by its necessity for a particular task, which is influenced by the number of domain-specific tasks in which human-AI collaboration is possible. This, in turn, affects the usability of HUX AI in varied environments, ensuring its usefulness throughout the day in a personalized smart device, or PSD. A task-specific environment is characterized by certain properties. Firstly, objects of interest, or OOIs, are a task-specific set of relevant objects, entities, or elements, which can be physical or virtual, and may have varying levels of importance or priority within the task. Secondly, events of interest, or EOIs, are a task-specific set of relevant actions, behaviors, or phenomena, including both expected and unexpected events resulting from OOIs, and can involve interactions between OOIs or changes in their states. These properties of a task-specific environment are crucial in understanding the context in which HUX AI operates, and how it can be optimized for effective human-AI collaboration. In the realm of human-AI collaboration, a research paper emphasizes the significance of developing an AI system that can effectively comprehend and interpret environmental context to enhance usability. The authors propose a system called HUX, or Heads-Up Experience, designed to optimize user perception and interaction with real-world or digital environments. HUX is built on three key components: environmental context, EC, desired features of AI for varied usability, and the heads-up experience itself. The environmental context, EC, refers to relevant background information and conditions of the task environment, influencing how objects of interest, OOIs, and events of interest, EOIs, are perceived and interpreted. This may include spatial, temporal, or situational factors. Desired features of AI for varied usability include spatial and temporal real-time scene understanding in a task environment, understanding user perception, contextual interaction using multimodal data, understanding, remembering, and recalling multimodal interaction, and future scope for multimodal outputs and actions. The HUX AI tracks only EOIs, confined to a task environment, ensuring efficient live computation by avoiding unnecessary spatial and temporal information. The heads-up experience integrates and optimizes human-AI collaboration to handle real-world or digital environments, narrowing the lines between humans and AI and enhancing collaboration and interaction. Overall, the HUX system aims to create a more efficient and effective human-AI interaction model by leveraging environmental context and desired AI features. The heads-up experience, or HUX, revolutionizes smart glasses by integrating artificial intelligence to create an immersive, interactive, and multimodal interface. This innovative system extends the traditional heads-up display concept, enabling users to engage with their surroundings in a dynamic and contextually aware manner. By consolidating various functionalities typically managed by separate devices, HUX AI has the potential to eliminate the need for smartphones and other gadgets, streamlining the user experience and facilitating intuitive interaction with technology. The HUX AI architecture, as illustrated in Figure 3, consists of integral components that facilitate the system's operation and flow. These components include data sources from various modes, data flow within the HUX AI system, data processing, and data flow for each modality. Notably, all input data modes are converted to text captions and descriptions, which are then integrated by the multimodal context processing engine using a prompt architecture. A key feature of HUX AI is its ability to trigger a multimodal context processing episode upon the creation of a new voice file or new utterance input. This episode collects the latest scene captions stored in the last and only used stack and retrieves the latest ROI caption, whose origin image is created simultaneously with the speech audio file. This sophisticated processing enables HUX AI to provide a seamless and immersive experience for users. In the HUX AI system, multimodal context processing is a pivotal component that integrates and processes textual representations from diverse input modalities, generating outputs in response to user inputs and dynamic environmental changes. This dynamic environment necessitates the user to accomplish a task of interest, with the system providing processed perception input and receiving user inputs. The system's architecture comprises the vision language model, specifically the mini-intern VL 1.52 billion parameter model, for image captioning, and the large language model, utilizing the Llama 3 8 billion parameter model, for all large language model instances, including multimodal context processing. Task-specific perception models, such as YOLO and printed circuit board defect detection, are employed to identify objects of interest and elements of interest. The core components of the HUX AI system involve processing multiple modalities, including user speech input, which triggers a multimodal context processing instance, and eye gaze information. The user's eye gaze is measured to produce a region of interest, enabling the system to generate outputs in response to user inputs and environmental changes. The system's ability to process and generate outputs relies on the integration of these components, facilitating the HUX AI system to provide accurate and relevant responses to user inputs and dynamic environmental changes. The HUX AI architecture, as illustrated in Figure 3, offers a comprehensive framework for processing multimodal data. It consists of four primary components: origin of multimodal data, data processing, multimodal context processing, and output generation. The origin of multimodal data includes various sources of input data, such as text, images, and audio. This data is processed through modules like data cleaning, normalization, and feature extraction. The processed data is then integrated into the multimodal context processing component, which, based on the Liu stack concept, efficiently processes sequential data to capture long-range dependencies and contextual relationships. The output generation component takes the processed multimodal representation and generates the desired output, which can be in text, images, or other modalities. Mathematically, the multimodal context processing component is represented as Z equals N Airy summation, M in M, gamma, M, F, M, X, where gamma, M, is the modality attention weight, and F, M, X, is the modality-specific feature extraction function. The Liu stack architecture optimizes modality attention weights through iterative updates. The HUX AI architecture addresses limitations of existing models by efficiently processing sequential data and generating context-aware outputs. In the real-time video feed filtering section, we delve into the process of extracting frames from a real-time video feed based on events detected by the real-time video analyzer. These events, visually represented by green boxes in Figure 4, are filtered and sent to the vision language model for image captioning. The event data is then combined with image captions and processed for context. The section highlights various types of events, including changes in object numbers, behavior, and custom-defined events specific to the application domain. This process enables the system to adapt to dynamic environments and respond accordingly. The section on page 17 delves into the application of video-based learning models, VLMs, for real-time event-based video context processing. It concentrates on detected events of interest, utilizing VLMs to analyze and comprehend the context surrounding these events. The figure depicts the expected outcome of this processing, showcasing the model's capability to extract relevant information from video data in real time. This approach enables the detection of events and their contextual understanding, which is vital for various applications including surveillance, monitoring, and data analysis. The figure illustrates the real-time event-based video context processing using virtual light field, VLM, for detected events of interest. It highlights the computation time of the previous frame, resulting in some events being missed until the VLM is freed. The process involves exporting these events as frames for context processing, allowing the engine to understand occurrences in real time while saving processing time. The approach also addresses the possibility of multiple frames being classified as events of interest during VLM processing, focusing on the latest frame after completing the current one. This hybrid approach is depicted in Figure 6, emphasizing the importance of efficient processing for real-time video analysis. Here is a refined version of the transcript. A hybrid approach for real-time event-based video context processing is proposed, combining computer vision and natural language processing to provide a comprehensive understanding of dynamic scenes in videos. The methodology integrates visual language models, VLMs, within an event-based processing pipeline, consisting of 3 stages: event detection, feature extraction, and context interpretation. In the event detection stage, salient events such as object movements or interactions are identified within the video stream. Feature extraction then generates a set of visual features that capture the essence of these events. The novel aspect of this approach lies in the context interpretation stage, where VLMs interpret the extracted features and generate a textual description of the events. This textual output can be utilized for various applications, including video summarization, object tracking, or generating captions for videos. The hybrid approach offers several advantages over traditional methods, including improved accuracy in event detection and better contextual understanding of complex scenes. The use of VLMs enables the system to learn from large datasets of videos and texts, allowing it to generalize well across different domains and tasks. By integrating computer vision and natural language processing techniques, this method provides a robust framework for understanding and interpreting dynamic visual content in videos. The authors underscore the importance of real-time scene analysis in identifying essential objects of interest, EOIs, within a scene, particularly when detailed image captions are unavailable. This is crucial for real-time computation. They then delve into task-specific scene processing, utilizing the same real-time video analyzer for EOI identification to enhance user perception visually. This involves temporally filtering out events and annotating the scene image feed with objects of interest, OOIs, relevant to the user's task. The benefits of this approach include providing a visual aid to the user by annotating the scene image feed, allowing the HUX AI system to understand the scope of task-specific OOIs, and enabling modularity to handle different tasks with unique sets of OOIs and EOIs. Additionally, this approach facilitates adaptive attention allocation, dynamic shifting of focus based on changing environmental priorities, attention restoration, and selective ignorance cultivation, which helps the user intentionally disregard non-essential information for the task. The author's approach enables the system to prioritize and filter out irrelevant information, improving task-specific selective attention, and ultimately enhancing user performance and efficiency. In the realm of human-computer interaction, enhancing the modularity of task-specific computer vision models is pivotal for detecting objects of interest, OOIs, and objects of non-interest, ONIs. By employing agentic behavior, these models can switch between different task-specific models with or without explicit user summons. This concept is illustrated in Figure 7, which showcases various computer vision models: Task 1, Task 2. Task 5 responsible for EOI and OOI detection in diverse scenarios. These models augment the user's visual scene by visually labeling OOIs, thereby serving as a visual aid for the user. This approach aims to boost the efficiency and accuracy of human-computer interaction across various contexts. The HUX AI system leverages the Vision Language Model, VLM, to perceive and empathize with user perception, facilitating understanding and empathy through shared image analysis. Both the user and AI system perceive the same image, which is passed to the VLM along with text instructions and annotations for context interpretation. This enables the language model, LLM, to interpret the scene and engage in conversations with users. The system's modularity allows for the seamless integration of task-specific models while retaining core components, as illustrated in Figure 7. This flexibility enables the HUX AI system to adapt to diverse applications. Real-time eye gaze processing is achieved through a parallel pipeline that processes eye gaze data alongside scene data. Figure 8 visualizes the origin and flow of eye gaze data, highlighting frames where new eye of interest, EOI, is observed and speech is triggered. The ROI gaze image is generated from the scene image and eye gaze data, which is then sent to the VLM for image captioning. The user's utterance is transcribed into text using OpenAI Whisper. This innovative approach enables the HUX AI system to empathize with users, understand scene context, and engage in conversational interactions. The system's modular design and real-time eye gaze processing capabilities make it an effective tool for various applications. The authors propose a novel approach to integrating eye gaze processing with scene processing in a parallel manner, as illustrated in Figure 8. This figure depicts the processing pipeline, where the eye gaze module and scene processing module operate concurrently, exchanging information to facilitate efficient and accurate visual attention modeling. The eye gaze module employs a convolutional neural network, CNN, to extract features from eye gaze data, which are then fed into a recurrent neural network, RNN, to model the temporal dynamics of gaze patterns. The RNN outputs a probability distribution over possible gaze locations, which is used to inform the scene processing module. The scene processing module, on the other hand, leverages a hierarchical graphical model to represent the scene's semantic structure, comprising objects, regions, and their relationships. This model is learned from a large dataset of annotated scenes, enabling the module to infer the scene's layout and object identities. The key innovation lies in the parallel processing of eye gaze and scene information, allowing the system to iteratively refine its understanding of the visual scene and attentional focus. This is achieved through the exchange of information between the two modules, where the gaze module provides attentional cues to the scene processing module, and the scene module feeds back scene context to the gaze module. Mathematically, the gaze module's output probability distribution is formulated as P, G, I, where G denotes the gaze location and I represents the input image. The scene module's output is represented as P, S, I, where S denotes the scene structure. The parallel processing is facilitated by the joint probability distribution P, G, AI, which is approximated using variational inference. The authors also provide an algorithmic outline of the parallel processing pipeline, highlighting the iterative refinement of gaze and scene estimates. The algorithm initializes with an initial gaze estimate and scene structure, and iteratively updates these estimates through a series of message passing steps between the gaze and scene modules. Overall, this parallel processing approach enables the system to efficiently integrate eye gaze and scene information, facilitating accurate and efficient visual attention modeling. In augmented reality environments, creating multimodal contextual memory is a complex process that integrates various input data. This includes spatial and temporal scene recreation, eye gaze data, and scene images. The raw gaze data and overall scene are used to obtain the region of interest, ROI, through cropping or segmentation, which is then fed into a visual language model, VLM, to generate text inferences. The scene image is also passed to the VLM to obtain image captions. These data are translated into textual form and processed by a multimodal context processing engine. The multimodal data and user context during interaction can be stored in a structured format, enabling later retrieval based on contextual cues using techniques such as retrieval augmented generation, RAG. The llama index is employed to execute this pipeline, leveraging agentic behavior to extract the class of object of interest from user input interaction. Figure 9 illustrates the process flow, demonstrating how the chosen scene image is sent to the VLM for image captioning and ROI processing. The ROI, obtained through verbal specifications or eye gaze, is also sent to the VLM for image captions. The agent extracts user context from conversation and sends all multimodal data to a large language model, LLM, instance to generate keywords, phrases, and other contextual cues. Figure 10 showcases the data structure of a multimodal contextual memory, highlighting its existence among other memories. Each data type in the multimodal memory data structure is described, including the object of interest obtained using YOLO. This comprehensive overview provides insight into the complex process of creating multimodal contextual memory in augmented reality environments. The multimodal contextual memory pipeline integrates various modalities to form a unified memory structure, as depicted in Figure 9. This structure, detailed in Figure 10, enables the storage and retrieval of contextual information across different modalities. The pipeline commences with the acquisition of data from diverse sources, which are then processed and integrated to form a coherent memory representation. This representation captures the contextual relationships between different modalities, facilitating more effective retrieval and utilization of stored information. The pipeline's integration process involves the fusion of modality-specific features, allowing for a comprehensive understanding of contextual relationships. This unified representation enables the identification of complex patterns and correlations across modalities, which can be leveraged for enhanced information retrieval and utilization. The contextual memory pipeline's design ensures that the stored information is organized in a manner that preserves the contextual relationships between different modalities. This organization enables efficient retrieval of relevant information, facilitating informed decision-making and improved performance in various applications. By integrating multiple modalities, the pipeline provides a more comprehensive understanding of context, allowing for more accurate and effective information processing and retrieval. The unified memory structure enables the pipeline to capture subtle nuances and correlations across modalities, making it an effective tool for a wide range of applications. In the context of human-AI interaction, the selective attention problem is a significant challenge that needs to be addressed. The proposed solution involves the use of an LLM instance to generate keywords and phrases for future retrieval, minimizing computation cost and time when processing user queries. The system stores image captions of objects or regions of interest along with their locations, scene image, and user-provided context through speech input. Metadata such as location, time, and device name are also obtained and stored. When the user refers to an object with contextual cues, the agent can retrieve the stored memories to provide relevant information. This approach offers reduced computation cost and time in processing user queries, as well as improved efficiency in retrieving relevant data. Integrating HUX AI into human-AI collaboration systems yields enhanced situational awareness, cognitive offloading, and multitasking support. In complex scenarios, HUX AI detects subtle environmental cues or threats more effectively than humans, leading to improved decision-making. By monitoring less salient task elements, HUX AI frees up human cognitive resources for higher-level decision-making. In multitasking scenarios, HUX AI manages parallel information streams more effectively than humans, allowing for improved performance. A comparative analysis of HUX AI's computer vision and manual video analysis reveals general alignment, but also some discrepancies. HUX AI identifies the highest variety of fruits at different timestamps, and both methods agree on the lack of consistent patterns in adding or removing fruits. Apples appear in 7 frames, disappearing once, and the orange has the most fragmented presence. Bananas dominate the frequency and quantity index, being the only consistently present fruit throughout the video. The selective real-time data computation is a crucial aspect of the HUX AI system. While all data can be stored without real-time computing, only frames with EOI are computed in real time due to resource and time constraints. This approach ensures efficient processing and utilization of resources in complex scenarios, allowing for improved performance and decision-making. The research paper presents a task-specific scene perception approach for visual enhancement using AR algorithms and deep learning computer vision. This approach is applied in a scenario where an engineer examines a PCB, as illustrated in Figure 11. The goal is to detect defects in the PCB using a computer vision model. The model labels the PCB, identifying possible defects among 6 classes. This process leverages LLM-based agentic behavior, which automates the model's usage based on user perception. The workflow, detailed in Table 2, begins with a user request for visual identification and is followed by the agent's visual inspection. The analysis of the circuit using the PCB HUD tool with a PCB defect detection model identified 3 defects, known as mouse bites, and provided their spatial locations. The agent explained that mouse bite defects are a type of defect characterized by small, rounded notches or bites taken out of the copper traces on a printed circuit board. The findings confirm the agent's capability in detecting and explaining defects using computer vision and language models. The interaction begins with the user inquiring about the contents of a printed circuit board, PCB, image. The agent responds by providing a detailed description of the PCB, including its components and features. Upon the user's request, the agent identifies any defects in the circuit, utilizing a tool called the PCB model. This tool returns a labeled image with 3 identified defects, all classified as mouse bites. The user inquires about the meaning of these defects, and the agent explains that mouse bites are imperfections or damages to the copper foil on the circuit board, which can cause electrical connections to fail. The agent detected 3 mouse bite defects. This demonstration showcases the agent's capabilities in conversational engagement, image analysis, and explanation of findings. When faced with an out-of-context question, the HUX AI system effectively identifies the question as out of context and responds accordingly, demonstrating its ability to understand contextual boundaries. This is made possible by the multi-modal contextual memory creation process, which is described in detail in subsection 4.6. This process is exemplified in Table 3, showcasing the system's ability to create a multimodal contextual memory in a real-life setting. For instance, when a user requests the system to remember an engineer they met for the first time, the system receives rich, multimodal information. Figure 12 illustrates this process, with the left panel displaying the scene image captured by a photonic sensor device, PSD, and the right panel depicting the region of interest, ROI, extracted by the agent using conversation context. This highlights the system's capacity to selectively focus on relevant information within the scene, leveraging conversation context to inform its processing. The creation of multimodal contextual memory is a critical aspect of the HUX AI system, enabling it to store and retrieve information in a contextually relevant manner. This capability allows the system to provide more accurate and informative responses to user queries, even when faced with out-of-context questions. In the context of human-computer interaction, robotics, and computer vision, A multimodal contextual memory storage system is demonstrated for a new engineer, Imam. Table 3 presents a detailed attribute description of Imam, a young man with dark hair and a beard, wearing a yellow t-shirt with text and graphics, seated in front of a computer setup in a tech or electronics lab. The scene description elaborates on the context, specifying Imam waving at the camera, giving a friendly and approachable appearance. The image depicts a cluttered desk with various electronic components and devices, including multiple laptops, a small robot, and a graphical interface on one of the laptop screens. The background shows a room with shelves filled with boxes and other items, indicating a workspace or lab. The object type is categorized as a person, and the user context is defined as a new engineer in the lab. The system stores information on the original scene image location and the cropped object of interest image location. A list of 25 retrieval keywords is provided, including Imam's name, appearance, lab setting, and various objects and components present in the scene. These keywords enable querying and retrieving the entire memory context, including the image, scene description, and object attributes. This demonstration showcases the system's ability to capture and store detailed information about a person, object, and scene, along with their attributes and context. The system's retrieval capabilities using a diverse set of keywords highlight its potential applications in various domains, including human-computer interaction, robotics, and computer vision. The HUX AI system is designed to mimic human selective attention in a dynamic environment, particularly focusing on high cognitive load tasks. The primary goal of this implementation is to explore the ability to pay multiple attention to things that the user might overlook due to their focus on a specific task. This technology aims to improve verbal recall of objects both temporally and spatially by engaging in conversations about overlooked items. The experimental setup for testing the HUX AI involves a dark background with fruits as objects of interest and introducing other objects at different times. The scope of the pipeline restricts its observational capabilities to increase the signal-to-noise ratio by limiting the set of objects and events of interest for accomplishing a specific task. For instance, when the user is focused on cooking, the AI should only detect events related to food items and not random objects. The real-time video analyzer restricts event detection capabilities for this specific task, while the visual learning model, VLM, can recognize all possible objects. The experiment aims to dynamically change the environment by spatially and temporally changing the objects of interest. This setup allows researchers to evaluate how well the HUX AI can adapt to these changes and maintain its focus on the task at hand. The experiment on page 34 simulates fundamental interactions between a user and an AI system. This setup involves randomly adding and removing fruits from a scene, with the AI responding to user queries about the environment and objects using eye gaze and multimodal data. The user, aware of the system's capabilities but not its technical details, poses questions to test its usefulness, including those listed in Table 4. The hardware used consists of 3 independent systems networked together to create the HUX AI system, with System 1 handling the user interface, running on Windows 11 Pro with 32 GB of RAM. In augmented reality environments, accurate event detection is crucial for enhancing user experience and interaction. To address this, a comprehensive system has been developed, comprising 2 main components, System 1 and System 2. System 1, the user interface and event detection hub, is equipped with advanced hardware, including an Intel Core i7 13th General CPU, 12 GB RAM, a NVIDIA RTX 4070 graphics card, and a 24-inch display with a resolution of 2560 by 1440 pixels. Additionally, it features a Tobii Eye Tracker 5 for collecting user eye gaze data. System 1's primary functions include converting user speech into text, displaying the augmented reality environment, collecting eye gaze data, and converting raw eye gaze coordinates into region of interest, ROI, images. It also captures the scene in real time through a connected camera and detects events using a model that processes frames in real time. System 2, the main hub, operates on Ubuntu 22 with 32 GB RAM, 16 GB VRAM, and an NVIDIA RTX 4070 Super graphics card, responsible for further processing and analyzing the data received from System 1. Although the hybrid approach depicted in Figure 5 was not utilized in this implementation, the system's architecture and components are designed to efficiently handle the demands of real-time event detection in augmented reality environments. The significance of this system lies in its ability to accurately detect events, providing users with a more immersive and interactive environment. By leveraging advanced hardware and sophisticated algorithms, the system can enhance user experience and interaction within augmented reality applications. The authors acknowledge potential limitations and areas for future work, emphasizing the need for further refinement and expansion of the system's capabilities. System 1 and System 3 are two distinct systems designed to perform specific tasks. System 1 is responsible for processing ROI images, collecting and fusing data with large language model (LLM) prompts, and converting text to speech. This system is powered by an Intel Core i9 general CPU and utilizes specialized software for each task. In contrast, System 3 is dedicated to scene processing, requiring an Intel Core i7 general CPU, 32 GB of RAM, and a NVIDIA RTX 4070 graphic card to manage the high video memory demands. Due to these intense requirements, scene processing is outsourced to System 3. The two systems communicate with each other to receive and process gaze images and speech-to-text data, facilitating seamless data exchange and processing. The technical specifications of these systems ensure efficient and accurate performance of their assigned tasks, enabling the integration of advanced computer vision and natural language processing capabilities. The communication pipeline receives raw EOI frames from System 1, processes them, and sends them to System 3 as image captions in real time. This process is limited by the compute-intensive nature of vision language models, VLMs, and large language models, LLMs, requiring parallel deployment across three systems for optimal performance. Notably, multimodal contextual memory was not integrated into this pipeline but was tested separately. User interaction involves pressing and holding the spacebar to provide voice input and capturing the user's gaze image upon releasing the spacebar. The EOI frames extraction operates independently, updating only with environmental changes. The user then waits for the AI response, which cannot be interrupted or paused in this prototype version. Trials revealed errors primarily in speech-to-text conversion and instances where the user's gaze fell outside the scene environment, highlighting areas for further investigation to improve system performance. In the context of human-computer interaction, the 11th screen of a system utilizing HUX AI was analyzed for its response to user queries. The system demonstrated an ability to answer questions, but often provided irrelevant responses when the context window was not effectively utilized. This issue is attributed to two primary problems: hallucination and forgetfulness in the LLM conversation. To address these issues, a multimodal context processing prompt architecture was proposed. This architecture aims to leverage both previous responses and new multimodal information to answer subsequent questions. It includes a general detailed description of the user environment, specific gaze information, human speech queries, and precise responses. An experimental demonstration of this system was conducted, as shown in Table 4. This table illustrates example user queries that can be posed to the system, along with the data sources or origins that the multimodal context processing can utilize to generate responses. This architecture aims to enhance the relevance and accuracy of the system's responses, mitigating the problems of hallucination and forgetfulness. A multimodal system integrates scene, gaze, speech, and memory data to provide contextually relevant responses to user queries. This system's capabilities are demonstrated through various user prompts, as shown in Table 4. For instance, when a user asks, "Do you see any fruits?" the system utilizes gaze and scene data to respond. When asked for recipes involving the observed fruit, the system leverages both gaze and speech data to generate a response. The experimental setup, depicted in Figure 13, consists of a user seated in front of a display showing a real-time scene feed. A laptop with supportive material is used to test the system's capabilities and the kinds of queries that can be asked. A hotkey, the spacebar, triggers the creation of new speech input and extraction of gaze data, which are then used to generate regions of interest, ROIs. Figures 14 and 15 illustrate the experimental setup from different viewing angles, showcasing the webcam employed to capture the live scene, connected to the computer. This multimodal system effectively utilizes various data sources to provide contextually relevant responses to user queries. The system's ability to integrate multiple data sources enables it to respond accurately to complex queries, making it a promising approach for various applications. The experiment in the isometric view, depicted in Figure 13, leverages the prompt architecture of a large language model, LLM, to handle multimodal context processing, as illustrated in Table 4. Prior to engaging with the HUX AI, users provide informed consent. The HUX AI is designed to enhance and interpret visual scenes, posing specific questions and providing answers related to the enhanced visual feed, thereby facilitating human perception by offering contextual insights, clarifying visual details, and enabling informed real-time decision-making. By retrieving data from the HUX AI memory in real time, users can reduce their cognitive load and improve their quality of life. The HUX AI's ability to store and process multimodal data overcomes the limitation of current memory storage methods, which are restricted to single modalities such as images, texts, or voices. The discussion section highlights the potential of the HUX AI to overcome human limitations in selective attention through human-AI collaboration. Although the current prototype has latency issues, these can be addressed in future iterations of the HUX AI. Overall, the HUX AI has the potential to revolutionize human-AI collaboration, enhancing human perception and decision-making capabilities in real-world applications. The research papers section on visual analysis presents a detailed examination of the experimental setup for a machine learning-based object recognition system. Figure 14 offers a view from behind, showcasing the camera and sensor arrangement used to capture and process visual data. Figure 15 provides a comprehensive overview of the complete scene, highlighting the spatial layout and environmental conditions under which the object recognition task is performed. The authors emphasize the importance of understanding spatial context and environmental factors in enhancing model accuracy and reliability. By examining these figures, researchers can gain insights into how variations in lighting, background noise, and object placement impact model performance. This section underscores the significance of real-world testing environments in validating the efficacy of machine learning models. The experiment's design allows for a systematic investigation of factors influencing model accuracy, informing strategies for model improvement and optimization. This visual analysis serves as a crucial component of the research, providing valuable information about the experimental setup and its implications for machine learning model development. The paper explores the potential of AI in creating multimodal contextual memory and retrieving it through contextual cues. This capability integrates multiple data types to facilitate a comprehensive understanding of past events, enhancing memory recall and decision-making. The authors highlight their work as a starting point for human-computer environment interaction to enhance human perception abilities. They identify current limitations, including the need for more environments to be tested. Future works include assessing multimodal memory retrieval capabilities in large-scale data, considering privacy limitations, and conducting studies on human-robot interaction with HUX AI and wearable robotics as a form of human-AI collaboration. The concept art in Figure 16, generated by DALL-E, showcases the integration of HUX AI with a wearable robot, comprising a snake robot and a manipulator, which enables seamless communication and manipulation tasks. This wearable robot, akin to a backpack, has the potential to augment human capabilities. The HUX AI system is designed to facilitate human-AI-powered drone collaboration, where the AI, informed by human perception, utilizes drones to aid human interaction with the environment. This collaboration can also encompass additional perceptions and manipulations. The system can incorporate teleoperated robotics, where the camera feed is sourced from remotely controlled robots, allowing HUX AI to interact with and perceive the environment through these robots. Moreover, the HUX AI system can be integrated with smart appliances, enabling seamless control of these devices by users. This integration has the potential to enhance the overall user experience and facilitate more efficient interaction with the environment. The incorporation of these various components and systems underscores the versatility and adaptability of the HUX AI system in augmenting human capabilities and enhancing environmental interaction. The HUX AI system has the potential to revolutionize human-computer environment interaction by enhancing user interaction with smart devices. It focuses on 4 key areas: understanding user intentions, way navigation, empowering differently challenged users, and aiding creativity and brainstorming. For understanding user intentions, GAZ-based actions using spatial reasoning can be employed to manipulate devices in familiar and unfamiliar environments. This integration makes user interaction more intuitive and efficient by leveraging the HUX AI system's ability to interpret and act on user intentions. In GUI navigation, vision language models (VLM) can be implemented in multimodal systems like HUX AI, presenting an exciting problem statement. The system can also be customized to process multimodal data according to each user's unique needs, empowering differently challenged users and facilitating a frictionless human-AI collaboration. The ability to store contextual, multimodal memories enables the fusion of diverse data types, aiding creative endeavors such as brainstorming. This approach mirrors human creativity, combining different insights to form singular, innovative ideas. HUX AI can support more holistic and imaginative problem-solving processes by integrating and synthesizing varied information. HUX AI is a novel system designed to transform human-AI collaboration by integrating multimodal interaction, task-specific environments, and contextual memories. This technology seeks to revolutionize human-computer interaction and environmental engagement. HUX AI's innovative approach combines 3 key components: eye gaze tracking, scene analysis, and speech input. This multimodal interaction enables more effective and intuitive communication between humans and AI systems. The incorporation of eye gaze tracking allows the system to infer user intent and attention, while scene analysis provides contextual understanding of the environment. Speech input, meanwhile, enables natural language interaction. By integrating these components, HUX AI creates a seamless and personalized experience, paving the way for future advancements in intelligent technologies. The system's task-specific environments adapt to individual user needs, fostering a more efficient and collaborative workflow. Contextual memories, which store and retrieve relevant information, enable the system to learn from user interactions and improve over time. The ultimate goal of HUX AI is to create a more symbiotic relationship between humans and AI, where the system can anticipate and respond to user needs in a more human-like manner. By doing so, HUX AI has the potential to transform various industries, from healthcare and education to transportation and entertainment, and revolutionize the way humans interact with technology and their environment. This section of the research paper provides a comprehensive overview of the relevant literature in attention mechanisms, object detection, and mixed reality applications. The authors draw on Treisman's 1964 seminal work on selective attention, emphasizing the importance of monitoring and storage of irrelevant messages. They also reference Deutsch and Deutsch's 1963 theoretical considerations on attention, as well as Levy's 1995 study on perceptual load as a necessary condition for selective attention. The authors then delve into state-of-the-art language models, specifically the GPT-4o model introduced by OpenAI, 2024. This is followed by a discussion on object detection architectures, including YOLOV 7, which has achieved impressive results in real-time object detection tasks. Wang et al., 2023. In the context of mixed reality applications, the authors review Microsoft HoloLens applications over the past 5 years, Park et al., 2021, and highlight the work of Farrison et al., 2020, on real-time object detection and tracking using HoloLens. They also mention the AutoRT framework, An et al., 2024, for embodied foundation models in large-scale orchestration of robotic agents. Finally, they reference Wang et al.'s N.D. G-Voila system, which enables gaze-facilitated information querying in daily scenarios. This literature review sets the stage for the author's proposed approach, which likely builds upon or contrasts with these existing works in attention mechanisms, object detection, and mixed reality applications. The research paper explores multimodal models, object detection, and knowledge-intensive NLP tasks, emphasizing the importance of integrating diverse data modalities to enhance performance in these areas. It begins by discussing the limitations of traditional text-based approaches in object detection and the benefits of incorporating visual and spatial information. The paper then delves into the development of multimodal models, highlighting their potential in improving object detection accuracy and robustness. The authors cite two prominent studies that demonstrate the significance of incorporating spatial attention mechanisms into neural networks for image classification tasks. Specifically, they reference the squeeze and excitation (SE) block, which adaptively recalibrates channel-wise feature responses, and the convolutional block attention module (CBAM), which utilizes both channel and spatial attention to selectively focus on meaningful regions. Building upon these concepts, the authors propose a novel attention mechanism, dubbed the Spatially Variant Attention Module, SVAM. SVAM dynamically generates attention weights for each spatial location, enabling the network to capture nuanced, context-dependent relationships between features. This is achieved through a lightweight, spatially variant convolutional layer that learns to modulate attention weights based on local feature patterns. The authors further introduce a multi-scale feature fusion strategy, which aggregates features from different convolutional stages to provide a more comprehensive representation of the input image. This fusion is facilitated by the SVAM, which adaptively weights the importance of features at each scale. Experimental results demonstrate the efficacy of the proposed SVAM module, with significant improvements in image classification accuracy on the CIFAR10 and ImageNet datasets. Notably, the authors observe that SVAM outperforms existing attention mechanisms, including SE and CBAM, while introducing minimal additional computational overhead. The authors also provide visualizations of the attention maps generated by SVAM, which highlight its ability to selectively focus on salient regions and objects. In conclusion, the authors present a novel attention mechanism that effectively captures spatially variant relationships between image features, leading to improved image classification performance.